this is the final video of this chapter. Okay, we are almost almost halfway to this course already. Okay, so this one will extend into the case of function of two or more random variables. So first, we're going to talk about the naive approach, which is the generalization of the one variable case. And second, we are going to talk about the special case of this one, which is the linear combination. And the special case of linear combination is called the convolution. Then we're going to talk about one-to-one and differentiable transformation. And the last one, we're going to talk about the linear transformation. So enjoy. So the generalization, okay. Suppose that in random variable we have x1, xn, we have discrete joint distribution, and we have y1 until ym. That is the specification, nothing else interesting. But what very interesting is that if we have g of y1 until ym, we have to find x1 until xn that passes the criteria that A. That is fi of xi is yi for all I. Okay, that is the same as the one variable case, nothing interesting. And we can define this one, and this one is the same. We just change from sigma into the integration with respect to the area of big A of y. Look at the first example. Suppose that the first two customers plans to live together. Let xi be the time that it takes to serve customer I. Suppose that x1 and x2 are independent with common distribution with this one. We have to find the distribution of the sum of the random variables. Okay. So that means we define a1, ay be something like this. We treat y as if a constant. So in the end, if we want to find gy must be the function of y. Okay. Let's consider looking at this one. Okay, so x1, x2. And x1, x2 plus is less than or equal to y. What does it mean? It means we mark y here, we mark y here, and then this is the area that we consider. That is, if we want to find the integration with respect to x1 first, that is, for each x2, x1 extended from what? From 0 to y, okay? Y minus x2, that is when we span horizontally. And if we want to span vertically, okay? Vertically, that is we have from 0 up until y. We take the integration 2 times, okay? And we get this function. Okay, so it's the same concept. We just that apply the integration, let's say twice in this case. So the special case is called the linear combination. The linear combination, which is that if we have x1 and x2 have the joint distribution and let y be something like this, then y has a continuous distribution whose PDF is dy, is the f of the inverse, okay? Of the inverse, it is the same, let's say the same formulas, okay? So let's ignore x2 for this. If one we know x2, this one is equal to be x1, right? And then we times this one, it is the, let's say, this one, the inverse. And then we differentiate. And we integrate up until x2. Because we have to find in terms of x2, and we use this to flatten out. Use this to flatten out. Okay? So let's see the proof. Okay. So ay be something like this. So gy is that we have to use the concept of flattening out. Okay, flattening out f1, x2. x1 from minus infinity to this one, and x2 for the rest of it. Okay. So let's see with this one. Let is just define new variables. So that we could write it something like this. Okay, we could we could write it. We could write it something like this. Okay. Or we could write the other way around. That's fine. Okay. So let's see. The special case of this one is called the convolution. Convolution is that we use the previous formula in order to find f1 of y minus c and f2 of c, and we integrate for all dc. It doesn't matter which one comes first because we can show that it is equal to this formula. Okay. So next one. Suppose that x1 and x2. So we have talked about the convolution. That is the sum of, let's say, two or more random variables. Okay. So the next concept is the order statistics. Order statistics, which is that we are not interested in the distribution of x1 up to xn itself, but we are interested in the maximum and the minimum. The maximum is a function of the random variables. The minimum is a function of the random variables also. So the subscript n here, it is the nth order. That is the max. And the subscript here 1 is the first order. This is the mean. Okay. So let's say we want to find the max. Probability of big Y of n is less than or equal to the Y. If the maximum less than or equal to Y, that means all variables must be less than or equal to Y. Right? And if it is independent, we can use this one. And we can differentiate into this formula. The same holds true. But this way we have to be a little bit adaptive, which is that if the minimum is less than or equal to Y, that means the others greater than or equal, but we could not use this information. That is, we're going to switch, okay? We're going to switch into 1 minus probability of y1 greater than y. That is, we have x1 up to xn greater than y. And this one, we can multiply it together and to the power of n. And we just take the derivative. So in the exam, okay, in the exam, I recommend, okay, I recommend, remember the CDF. I recommend remember the CDF, not the PDF, because PDF is the derivative and it is more ugly. Okay? So remembering the CDF and use the derivative concept applied in the test, and you will see that it is much more convenient. But if you want to find the joint distribution of the mean and max together, that is, we have to find what? We have to find the probability of y1 less than or equal to y1, y big N less than or equal to yn. And we just slightly modify this into this one, okay, into this one, and into this one, okay? And then for this one, we know and for this one, okay, and for this one, we know this one, okay, but this one, do we know? We just have to separate it out into n terms like this. And then with this one, we can multiply it together. And we have this kind of products. So usually in the exam, we do not ask this kind of formula. We do not ask you to remember this kind of formula. But if you see on the test there, you have to make sure that you know of this step. Okay, you have to know of this step, but you are not required to remembering it. If we take the derivative twice, it's gonna be ugly formula like this. Okay. So the example 3. Suppose that the n random variable x1 up to xn form a random sample from the uniform distribution on intervals 0 and 1. So find the PDF of the range of the sample. What is the range? The range is the maximum minus the minimum, right? The maximum minus the minimum. That is, we have to find the joint distribution first, and we have this from the last slide. Okay. And for this one, we use the concept of, let's say, the convolution. The convolution, where it's the negative one, right? So the G of C and C plus W. Okay, C and C plus W. Because we want to find the W. But C plus W, if the range is W, the minimum is C. It's gonna be, the maximum is gonna be C plus W. We substitute this. Okay, we substitute this. And then if we want to flatten out with just only the range, so what are we going to do? We are going to integrate with respect to C because we have to get rid of C. It seems like we do not have to get rid of C because no C here, right? But it is a function of C. We have to get rid of C anyway. That is, we integrate this one with respect to DC. But how do we get respect to DC? We integrate with 0 up until 1 minus W. Because the range is between 0 up until 1 minus W. And we get this function. Okay. So let's say 2 special cases that are interesting and are often used rather than the intuitive or naive one. Okay. So the first case is one-to-one and differentiable. That is, we have the inverse. We have the inverse and differentiable. The concept is the same. F of x1 up to xn, except this one. Except this one. So rather than finding just one variable and take the derivative, we have to find many variables, and we can rearrange into this matrix J. Okay, not matrix J. Let's say this matrix that here. But this is a matrix. We cannot do anything. But we want just only a single number. The best way to reduce this is to take absolute of the J. That is the absolute value of the determinant of J. Okay. The second case is the linear transformation. The linear transformation is simple. Okay. So Y, we know that Y this is the inverse, right? The G of Y is, let's say, the F of X and the determinant of the A negative, because X is A inverse of Y. We assume that A has the inverse. Okay, if A doesn't have the inverse, we have to go back to the intuitive one, the naive approach. Suppose that it has the inverse, so it is Fx times the determinant of A inverse. But remember, what is the X? F of A inverse times Y. And what's the determinant of A inverse? It is 1 over the determinant of the A. Okay, so these are the two switches that it is very similar. Once you understand about the previous one, you can understand this one very easily. Okay. You can understand this one very easily. My mouse is very low on the battery. Okay. So what's next? You have mastered all the concepts. It's a random variable and distribution already. So it's time to go to the practice. So in the next 3 videos, we're going to first see the big picture, and then we are going to drill down the exam strategy in the following 2 videos. So see you next time.